Hello everyone, my name is Laura Pu. I'm a PhD researcher at Ghent University. The work that I will present today is a collaboration between two research groups in the university. There's Susan Laboratory, who is more expertise in mechanical testing, and the Sustainable Material Science, who has more expertise in the material part of the story. The framework of my talk of today is the plan of Europe to create a hydrogen grid of 60,000 kilometers among 25 countries in Europe. And to achieve that goal already by 2040, almost 60% of that will be repurposed pipelines. But I don't think I will tell something new to you if I say that hydrogen can reduce the material characteristics. So in previous research, we already saw that hydrogen can cause a loss in ductility, a loss in fracture toughness, which are parameters on which material selection is based, also the design of the pipelines. So that's why we have the HyFit projects in our university. And there, the strategy is to combine mechanical testing with numerical simulation to, in the end, help the prediction of the toughness service of the pipelines. The numerical simulation is based on the model created by Verbeken. It's a coupled model which includes the fusion, the damage, and the degradation caused by hydrogen. And those are being calibrated and validated by mechanical testing that we do in our lab. With this project, we further include also the wells, and we try out different scales to see the effects of size there. My focus is mechanical testing, and today I will go deeper into the SENT lab scale testing of the heat effective zone in pipelines. So first I will introduce you a bit into the material that we're using. The pipeline material is L485 steel, which is similar to an X70 steel. What do we see in this material? We see bands, hard bands distributed through the thickness. Those black bands contain perlite, but also hard inclusions. If we have a look at the heat affected zone of the girth wells, we have a heterogenic microstructure. First, close to the wells, we have a coarse grain heat affected zone, further fine grain, and then we go to an intermediate one that involves further into the base. For the three parts, the base material, the heat affected zone, and the girth wells, we did we measured the hydrogen uptake, and we see a little difference between those three parts of the material. Further, I will tell you a bit more about the toughness testing. First, we will pre-charge our specimens. Then we will do our toughness test, which is a single edge notch tensile test. And then we analyze based on the things we measure during the test. Also afterwards, we look into the microscopy and the cross sections of those specimens. First, the specimen at 10 by 10 cross section, single edge notch tensile specimen with a length of 100 millimeters. We try to position the pre-fatigue crack tip in the heat affected zone as close as possible to the well. So we try to position it in the coarse grain heat affected zone in the depth of 3 millimeters. So according to the standards. And then our test itself, we test after 24 hours of pre-charging. We do the test ex situ because we later on in the project want to compare it with the larger scale specimens, which are where we would have practical issues if we try that in situ. So that's why we here also already do the ex situ to be able to compare. During the test itself, we use clip gauges at different heights to, in the end, calculate the crack tip opening displacement of the test. And we also use DCPD. So we apply a constant current on the specimen, and we measure the voltage away from the crack and also over the crack. That's where we can then retrieve the crack road during the test. So if I now go to the results, for the reference test, we did 6 specimens. For the hydrogen one, we did 5 already. And we see that the normalized force, that there's a slight drop for the hydrogen recharged specimens. But most importantly, we see that the normalized force drops faster than the reference specimens. Maybe more interesting is if we look at the resistance curve. There's one point that is interesting for us. It's the initiation point. And we see that even with the existing tests, there we also have already a drop of the toughness at the initiation point of the crack road. Then looking at the fracture surfaces, there, of course, the main focus is the crack road to see what's the difference there if we include hydrogen in our specimen. If we zoom in the start of our specimen, there we see a shiny band of the pre-charged hydrogen specimens. We go deeper into that band with SEM, we see quasi-cleavage and small cracks. This behavior can already explain why we have a lower toughness at the initiation point. And of course, since we're dealing with a heterogenic specimen where we as well have the weld, the heat-affected zone, and the base material, we wanted to see how the crack evolves during the test. And also there, we focus on the crack roads. And what is remarkable there is that we have a crack deviation in the hydrogen specimen. So the crack deviates away from the welds and goes through the base material. Now we question why this happens. Why do we have this deviation of the crack? The first hypothesis is if we look at the hydrogen concentration, we already had a different distribution of the hydrogen concentration because we extracted cubes 6 by 6 by 6 and charged them under the same conditions which were used for this test as well. And we saw different concentration for the base material and for the heat-affected zone and the weld material. This is not the only thing, it's in combination with a softened zone that we see, a softened zone at the border of the heat-affected zone and the base material. This can maybe explain that we can have more dislocation mobility in that area in combination with a slightly higher hydrogen concentration can be enhance in that region the effect of hydrogen. A second hypothesis is if we look at the fracture surface of the hydrogen charged specimen, that we see that there are regions of quasi-cleavage around inclusions. And that's the crack might link those regions, might link the inclusions during growing. So it's always searched for the weakest link in the pots in ahead. So to take a small recap of what I just presented, we tested on the heat-affected zone by single-edge nuts, tensile testing, and we saw reduced toughness of the hydrogen recharged specimen, which can be linked to the quasi-cleavage and the initial crack front, with also the small cracks that we observe there. Looking at the cross sections, we see deviation of the crack roads where we have multiple hypotheses. Thank you for your attention.